Okay, in this section 34.6, we'll look at refraction theory. I'm not going to get as deep as the book does, but I'm going to cover 2/3 or so of what they go over. Initially, the book talks about how at its a interface, say we've got here and some little ant is right here or something like that. I don't know. We're just going to draw a little ant. It's so small we're going to draw it as a blob. And then we've got, say, light, a lens right here. Light comes from that ant. And it would actually form an image inside here. Right about here. Now the question that really is interesting is, what happens at this interface? Here, 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 and here, what happens? Why is one bent more than the other one? And I'll basically tell you it's a function of the angle. Here it comes in pretty much straight. So if it comes in pretty much straight with this line, that's like a mirror. It goes in at this angle and it's not refracted. Snell's law is valid at every ray entering and exiting, but we don't do it in this example, and exiting a lens. Snell's law is valid. Here, we've got much more angle going in with respect to the normal. It's bent more. You got it bent like that. Here, you make the normal. It's bent more like that. So at each point, you would have to calculate it. And they pretty much kind of go through and with this for the example. But what I want you to get from this is know that when you have an interface between two different mediums, it could be water to your eyes, it could be water to air, water to glass. You could fill your binoculars with water and they'll form an image at a different spot. You might have to hold them out further. Okay? If they even form an image. At each interface, Snell's law is valid. N1 sine theta 1 equals N2 sine theta 2. So that's what they're using, and that's what you got to remember back in your mind. What's causing all this? The relationship, how when light goes from one medium to another, effectively slowing down, it bends. Or when light speeds up from one medium to another, slower to a faster medium, it bends the opposite way. All right? That's the basic idea here. So, the book goes through, on the next page, it talks about, and they derive a little bit of stuff. And basically what they end up coming out of this is, what I'll say is for a thin lens, but we're not going to take into account curvatures and anything like that. There's a relationship that says that the object distance, 1 over the object distance, plus 1 over the image distance equals 1 over the focal length. This is the thin lens equation. This is known as. And this is the one that gets used a lot. Now this assumes thin lens, we're not worried about curvatures. Now you can do this, take into account the curvatures on each side. And the curvature of the lens, and you have to do this when the curvature on one side is not the same as the other, because one side of the lens will focus more or less than the other side. You can have it could be converging on one side and diverging on the other. But if you take that into account, you've got to take into account the radius of that lens. And of course, what the lens is made of, water, glass, or whatever. So take that into account. You say 1 over the focal length equals n minus 1. There's that Snell's law coming into play. 1 over the radius on the first side, 1 over radius on the second side. And this will let you calculate or determine the focal length of that lens. Once you know the focal length of that lens, you put it here, and once you know object, you can find image, or if you see where the object image is, you know how far away the object is. Okay? This is sometimes known as the lens maker's formula. Why? Because it tells the lens maker, if I want a certain focal length for this lens, I just need to make sure I have the radiuses on one side and the other side specifically what I want. And I know what material I'm making it out of. Diamond, water, plastic, acrylic, or just regular old glass. Regular old glass. Okay. These two can be used together. Okay? Now, honestly, if you look at this, the book has some really good examples. Example 34:12. If you work through example 34:13, the magnifying lens there, they're trying to find the focal length of a magnifying lens using this, using the lens equation. These are really good examples. I'd ask you to work through them. See if I want to say anything. Only thing I will say here is R1, I'll say radius is positive if you're doing convex to the object. Now I'll put that in circles, meaning positive. Negative if concave to the object. Negative if concave to the object. We can do some rules about sides and stuff like that. You'll start to notice that as you go along, as you read your text. Bottom line, this is the equation from that chapter. I mean, there's a lot. It's kind of long and stuff, but it's just this one, applying it here and applying and doing examples. These examples, honestly, are fairly straightforward. When I used to teach high school, my high school kids got these pretty well. This would take a little bit extra, but this one, high school kids can get this. You guys are smart. You're calculus physics students. Honestly, I think you can go figure this out from looking at the book and going from there. I know these videos get long. The previous one is about 30 minutes. And so what I'm going to do is just say, I'm done here. Unless there's any questions, of course. Any questions? Before COVID? I'm not going to do that. Since I don't hear any questions, for some reason, I'm going to assume you don't have any. If you have a question, of course, shoot me an email, text me. You guys have ways to communicate with me on this. But go through the book, look at the examples of the book. I think it's fairly straightforward.